Hello, global supply chainers, and welcome to our second SC2x live event. Today, I'm pleased to have Milena with me. Welcome, Milena. So, Dr. Milena Janjevic is a postdoctoral associate at MIT Center for Transportation and Logistics, and she's also part of the Megacity Logistics Lab. She is a polytechnical engineer and holds a PhD in transport and logistic engineering from the University Libre de Brussels in Brussels, Belgium. She's also a lecturer there at the Center for Mobility Studies. Her current research focuses on urban logistics and last mile delivery, with particular focus on distribution network design in the context of e-commerce, deliveries, and urban freight logistic policy. We are really happy to have you here today, Milena. Welcome again.
Thank you.
Okay, so the plan for today is the following. So up to this point, we are almost in the middle of the course. So we're already presenting 4 weeks of content. And in these 2 weeks of content, what we covered mainly was about network design. So basically, the first 2 weeks of the course was network design. And the topic of this live event is going to be network design. So Milena is going to be sharing with us some experiences about implementing this type of project, but mainly covering last mile distribution network design. Okay, without further ado, Milena, so the floor is yours.
Thank you. So hello, everyone. I was asked today to give you some insight about some of the work that we are doing in a Megacity Logistics Lab with regards to the last mile distribution network design, which focuses mainly on urban markets. Before going into a further description about the work that we are doing, I will first give you just a short overview of why do we particularly focus on these urban markets and what are some of the challenges that we encounter there, and basically why so much of our work is focused on this particular part of supply chain. So the first reason for that is that we are living in a urban world. So today we have half of the urban population that lives in urban areas. This generates around 80% of global GDP. But as we look at the projections, the urban economic story is becoming even more concentrated. So this chart shows you the projected cumulative contribution to GDP growth between 2007 and 2025. And we can see that in 2025, first 100 cities, first 100 largest urban areas in the world are expected to account for 35% of global growth, and only 600 of them are expected to account for 62% of global growth. And when we look more closely to these 600 cities, we can also see that although they account for only 25% of the global population, they account for 60% of global GDP. What this means is that the increase in both the urban population and the GDPs will result in increased demands for goods in urban areas. So the demand for urban logistics is increasingly high. And this will bring some specific challenges, especially when we are transitioning towards these large megacities, which are typically highly congested areas. On the other hand, not only is the demand for urban goods mobility growing, but we also witness a fragmentation of urban deliveries. So on the first picture on this slide, you can see a container ship, and this illustrates that on the long distance transportation, we have increasingly consolidated transportation. So with, for example, container ships that can transport up to 15,000 containers. However, we can call this kind of a massification on the long distance freight transportation. But then when we look at the last part of the supply chain that occurs in urban areas, here, due to some trends, notably e-commerce, we witness a atomization in the urban leg of freight transportation. So this will generate an increase in number of vehicle trips, disproportionately to the increase of the overall demand for urban goods. On a city level, this will, of course, have impacts in terms of congestion, in terms of pollution, but it will also present some specific challenges for logistics companies that have to operate in these environments. And so to illustrate some of these challenges, I have two questions that I would like to address to you. So the first question is related to the cost effects of the last mile logistics. So please, in your opinion, what is the percentage of transportation costs that occur in the last mile?
Okay, so the poll is open. You can reply, and we are getting some results. So the poll should be in the right-hand side of your screen. Please select the one that you believe is the correct answer. So the question is, what is the percentage of transportation costs occurring in the last mile? So far we have 12 people. So most of them are answering that 28%. Is this something that you were expecting, Milena?
Yes, so 28% is indeed the average cost of transportation costs occurring in the last mile. So your answer is correct. This will, of course, depend on the type of supply chain that we're considering, but on average, it is 28%. This is a very large portion of costs. And just to illustrate the cost intensive nature of the supply chain, we can, for example, look at this slide here that illustrates one particular supply chain for textile industry that originates in India and goes to Europe, to Paris in particular. So we can see that there is a set of different links between production facilities, transshipping facilities, and different transportation services that are employed. And when we look at the urban leg of this particular supply chain, we can see that in terms of distance, it will account for around 1% of distance, and it will account in this specific case to 25% of logistics costs. So companies are looking into ways of optimizing this part of supply chain and decreasing the costs relative to a last mile. To illustrate the complexity of the optimization of last mile logistics, I have another question for you, which is related to the way that we can sequence different stops. So let's imagine that you have 5 vehicles that are departing from one single depot, and you need to serve 50 customers. And you can sequence these customers in many different ways. And the question is, in how many different ways you can sequence the stops of these 5 vehicles towards these 50 customers. So here we have 4 different choices, and we're expecting your best guess.
Okay. Are we talking about more or less a common, typical
yes.
last mile operation? So 50 customers, something reasonable. 5 vehicles, maybe just a small fleet, but let's see some of the answers.
So yes, here we have a rather small fleet of 5 vehicles, 50 customers, so 10 per vehicle, which is much less than we usually serve, but you will hopefully see that this is already a quite complex problem to solve.
Okay, so if you haven't answered the poll yet, please do it. So we'll share the result immediately. So we're getting some results. So 40% more or less of the people are saying the third option.
The third option. So actually, it is the fourth option.
The first option.
The first option.
Yes.
Okay.
So 10 to the 50.
Okay. So actually, it is the fourth option. So it's 2.4, 10 exponent 70 possibilities. So which is a lot. Indeed, only for 5 vehicles and 50 customers, this is the number of possibilities that we have. We can then take a real-life example to illustrate this complexity, and we can take that of UPS. So UPS does not deliver 10 customers per vehicle route, but an average on 120 delivery stops per route. And if we look at the slides now, we can see a very large number with a lot of zeros that I will show you right away. So according to the counting of these little zeros, this is actually an order of magnitude of 10 exponent 198. So This shows you the complexity of optimizing last mile operations. And just to give you an overview of how this optimization actually can affect the costs, let's again take an example of UPS. So they perform around 55,000 delivery routes in US per day. And if you were to apply a cost reduction of just 1 mile per route, this will generate 50 million of annual cost savings in the US. So companies have, it is in their best interest to indeed make sure that the last mile part of their supply chain is well optimized. Yeah. So in order to adapt their distribution strategies to these particular challenges of last mile, we can work on several areas. One of them is distribution network design, and this will be the focus of our events today. But we can also look in vehicle technologies and some measures that are more relative to, for example, operational planning. So let's go directly into distribution network design and see some of the ways that companies can optimize their networks in order to best adapt them to last mile environment. So when we think about last mile distribution design, we are thinking about several different decisions that need to be made. One of them is how do we locate facilities? The second one is how do we define service areas? And the third one would be what type of vehicles we use to actually serve customers in urban areas. And we can underline several, let's say, archetypes of network designs that we can deploy in urban areas. So here you see 3 different possibilities. The most basic one is the first one, which is a single tier system where we have one distribution center that is typically located in the outskirts of the city and that will serve individual customers with vehicle routes directly departing from the distribution center. However, when we look at these megacities and these large congested areas, we also see that it's typically more efficient to introduce a second layer of consolidation or a second layer of facilities. We can refer to them here as satellite facilities, for example, and these are the small squares that you can see on the scheme. And so here we have a 2-tier system, so a system that is composed out of 2 layers of facilities. And in these 2-tier systems, we can have 2 different options. So either individual customers are only served with vehicle routes departing from satellite facilities, or we allowed for a mixed system where the distribution center can also serve some individual customers. Introducing these multi-layered systems, so 2-tier, 3-tier, or more tier systems, brings some advantages. So it allows us to increase the vehicle utilization, to form more efficient routes, and consequently reduce the number of vehicles that are required and the costs. But also on a city level, it allows us to reduce the pollutant emissions, fuel consumptions, congestion rates, and the time that vehicles spend in traffic. And so the illustration that I will give today of one project that our lab has worked on is relevant to a 2-tier system in a urban area. And here we take an example of a major Brazilian e-commerce company that operates a multi-layered distribution network in the country. So we can look at their distribution network on several levels. So on a country or state level, they will typically have large fulfillment centers that concentrate all of their inventory. So this is where all of the order preparation takes place. But then if we look at the city level, they also have a multi-layered 2-tiered system. So an example here is relevant to Sao Paulo. They have one distribution hub that is located in the outskirts of the city, and they have 7 operational centers, which are, in fact, those satellite facilities that we have introduced in the previous slide, and that allow to serve as locations from where vehicle routes depart. So Just to make sure that this is clear, the operational centers are typically only performing transshipment operations. So in this particular setting, they do not hold any inventory. They are only performing transshipment operations from large vehicles to smaller vehicles that are more adapted to the urban environment in which they have to perform last mile delivery. And to give you an indication about the size of the problem, so this particular company delivers around 15,000 customers on a daily basis. So the project that I will refer to was how do we redesign their last mile distribution network in order to minimize the overall cost of operations. So here we focus on what's happening on a city level. So again, distribution hub operational centers. So we can look at some of the decisions that are typically made in network design problems. And to introduce them, let's look at this particular example. So the first level of decisions that we have to make is relevant to the locations of different logistics facilities. So this can refer to both distribution centers and satellite facilities. And here we typically have a set of candidate locations that we have identified and that can be suitable for implementing these logistics facilities. So in this particular case, we had around 200 potential locations. So you can see this as small dots on the map. And the location decisions are aiming in establishing which of those 200 facilities should be activated and which should not be. So in this particular case, we ended up with the following configuration. So this is one of the scenarios that we have analyzed. And so in the left side, you can see a real brown dot. This is actually the distribution hub. And then we can see a number of satellite facilities that were located throughout the city and that are used for this last mile part of the operations. The second type of decisions that we can make in the network design problems and that we are making is relevant to service areas. So here we have an entire city that presents different demand patterns. And the idea is to basically segment the city into a number of service areas and to define which service area should be served from which particular facility. So here in different colors, you have different service areas, and each one of them is attached to a specific logistics facility. So as you can see here, we are in a multi-tier mixed network where we have some of the customers that are served through a distribution hub, while others are served through satellite facilities. And so these service areas are typically fixed. So given that the network design problems are strategic problems, so we will not redesign our network on every day. We will only do it once every few years, maybe. We will typically define service areas that are fixed. So each facility will serve one particular part of the city. We can introduce additional level of complexity and introduce some variability on a daily basis if this is necessary, but this is something we can discuss later. And then the third type of the decisions that we are trying to make in network design problems is with regards to the modal choice or the type of vehicles that we want to deploy to serve each of those service areas. So here again, in the specific case of this e-commerce operator in Sao Paulo, we had 3 different types of vehicles that are presented here by different colors. And the idea is to define for each particular segment of the city, and that segment can be a neighborhood, it can be a zip code, it can be defined in any way that we or the company wishes to define it, which type of vehicle is most appropriate to serve customers. So as you can see, on the one hand, we define the locations. On the other hand, we define the service areas. And then within each of the service area, we allow for potentially different types of vehicles that can be deployed. So this gives you just an overview of the type of the decisions that we are trying to make in network design problems. And now we can go more into detail about the type of methods that we are employing to address some of these decisions. So typically, in order to model multi-tier distribution networks, we used mixed integer linear programming. So when we look at typical mixed integer linear program, we have on the one hand decision variables, and then optimization objective, and then constraints. Decision variables relative to this specific type of problems are relevant to the three types of decisions that we are making in network design, namely facility locations, service zones, and modal choice. So in order to model these for the first part, which is network architecture and defines active facility locations and their type, we will usually use binary variables. So for example, for each of those 200 facilities that we have identified as potential facilities that can accommodate either distribution centers or satellite facilities, we will define one binary variable that will take a value 1 if the facility is active, or 0 if it's not. For the facility influence areas, we typically divide the city into a set of discrete segments that, as I mentioned, this can be zip codes or neighborhoods or any other unit of geographical analysis. And for each of those specific segments, we use one typical binary variable that signifies if a certain segment is allocated to a certain facility. And the third one is relevant to modal choice. Here, a very similar approach. We use binary variables to assign each of the city segments to a certain vehicle type. So these, as I mentioned, correspond directly to the three types of decisions that we are trying to make. And the optimization objective that we have used in this particular project was a minimization of total costs of operation. So these total costs can contain several categories of costs. So there is indeed the cost linked to routing and last mile distribution, but also costs relevant to vehicle, equipment, facility, fixed costs, handling costs, etc., etc. We can also think about ways of extending this optimization objective. So we can, for example, include other objectives such as maximizing the total market reach, or maximizing the revenue or the profit, or decreasing the time that is required to reach certain customers. And we can also think about multi-objective optimization, where we integrate several of those objectives into a single objective function. However, most commonly, the cost that we are looking at, the objective function that we're looking at, is relevant to the cost minimization. And then we will also include a certain number of constraints in our mixed integer linear program. And these constraints are, of course, relevant to the feasibility of solution that we're developing, but also reflect some operational constraints in terms of carrying capacity of vehicles or capacity of facilities, because each vehicle or facility can only accommodate a limited number of shipments, and this is something that we want to include in our model. In a more advanced approach, we can also, for example, include vehicle access restrictions. So typically in some urban areas, there are access restrictions relevant to the vehicle size or the environmental performance of the vehicles that can be used in certain areas. And so this is something that we can also include in our mixed integer linear program. And so when we look at this this program, you see that we have actually two types of decisions that we are looking into simultaneously. So one is relevant to the location, and the second one is relevant to the routing, because in order to have a full network design problem, we need to simultaneously look at the location of different facilities and the routing of the vehicles from those facilities towards the end customers. And so this brings us actually to a category of problems that is called location routing problems, and that simultaneously looks into those two types of decisions. So We can break down this type of problem into two sub-problems. So the first sub-problem that we can look at is a location allocation problem. So here you have a very simple example where we have, again, a set of candidate allocations for distribution centers. So these are noted by D. And there we have also a set of customers that need to be delivered. So in a location allocation problem, we are typically looking into which of those candidate locations for distribution centers need to be activated. So here we have two of them that are activated. And how do we allocate different customers to those distribution centers? So which distribution center should serve which customers? And we can look at the formulation of this problem. We can again formulate this as a mixed integer linear program with a certain number of decision variables that are relevant to the location and allocation. However, what we notice is that when we move from this very simple toy problem that is presented here on the screen to real-life instances that contain a very large number of customers, the problem becomes NP hard, or in simple terms, very hard to solve. Very hard to solve means requires a very long computational time in order to get to an optimal solution. Another problem that is integrated in a location routing problem is the vehicle routing problem. And so this brings us back to that discussion about in how many ways we can sequence different customers within one vehicle route. So you have seen that there are many different possibilities. The reason for that is that we will define for each potential arc between two customers a separate decision variable. So this problem can become very hard to solve and very time-consuming to solve to optimality. So we have here two problems that are very hard to solve, and we want to combine them. And when we combine these two problems and we come up with a single formulation, what happens is that for real-life instances where we have, for example, thousands of customers, so we've seen 15,000 customers in the case of this Brazilian e-commerce company, this problem becomes impossible, intractable to solve. Again, let's think about this, the number of possibilities that we have for vehicle routing, and we can add to that the number of possibilities that we have with regards to facility locations. And so this shows you very clearly that if you want to combine the two problems, this becomes impossible to solve for real-life instances. And so this is where a lot of the research that we're doing in our lab comes into play, because we are developing techniques that allows us to simplify these problems and to formulate problems that are possible to solve while maintaining all of the complexities of the urban environment. And so one approach that we are commonly using in the projects that we are currently working on is called continuum approximation. And so continuum approximation allows us to basically combine these two types of location routing problems, but to bring them back to a simple location allocation problem. And so the basic idea behind the continuum approximation is that if we have some characteristics of demand that are satisfied in some hypotheses, such as, for example, that we have a homogeneous stop density of within a certain area, we can make some approximations. So, for example, we can estimate the average distance per stop for an area with a given density, with a given size, and considering a given distance to a serving facility. And so we can introduce additional elements, for example, global service time for vehicles. So we can say, for example, all of the routes need to be under 8 hours, vehicle carrying capacities, and different speeds. But at the end of the day, we are able to establish closed form formula for these for vehicle routes, and to actually approximate the cost of an optimal vehicle route in a given setting without performing the explicit vehicle routing towards each customer. And so this is something that is very interesting for the network design, because network design is a decision that is taken on a strategic level. So we do not have to basically establish each specific vehicle route towards each individual customer. So we only want to have information about how the cost of these routes will affect other decisions with regards to the location and the definition of service areas. And furthermore, in the case of an e-commerce company, for example, the specific demand will change daily. So we will never have the exact same 2 customers that are located in the same area. We will have variable locations for the demand. So we do not want to solve the problem for a specific instance of demand. We want to solve it for a average demand scenario, for example. So as I mentioned before, these approximations work, but they only work if we are able to enforce a certain number of hypotheses. So, for example, that the demand density is homogeneous in a zone that we are considering. However, when you think about a given urban market, this is rarely the case. So typically, there are areas of the city that are more dense, that present high population density, and that will therefore present a higher density of the demand. On the other hand, different areas of the city will also have different characteristics in terms of infrastructure. So some areas will be typically characterized by very small streets, narrow access and one-way streets, while others will be characterized by different infrastructure. And so if we want to apply this approximation directly to the whole service area, we will not be able to capture the granularity of those characteristics and the characteristics of each of the zones that we are considering. So what we are doing in order to still be able to capture the urban geographies and the demand patterns is that we segment the city into a certain number of areas. So we have one area here. We can see the outline of the service area in red, and we apply sort of a grid to this area, and we define a certain number of discrete demand zones. So each of these small pixels here, we refer to them as pixels, will be defined as a specific area. And so as a next step for each of those demand pixels, we will define a certain number of characteristics. So we can look at the demand density, so how many customers or how many stops do I have within that specific pixel. We can look at the drop size, how many items do I deliver per order, per stop. We can look at the volume of the deliveries. We can look at the infrastructural properties of each segment, and we can look at things like vehicle speed, etc., etc., etc. So we will define for each of those specific segments all of these parameters, and we will use that as an input to our model. And just to provide you an illustration of that, so here are a few maps that we have made for this Brazilian e-commerce company. So the first one is relevant to demand density. You can see that, for example, the areas that are located in the city center are the most dense. So they are with the red and orange colors, and as we move towards more peripheral areas, the demand density decreases. We can then use GPS traces of vehicles to define travel speeds within each segment of the city and use that as input data. And we can also look at some infrastructural properties of the network. So one of them is, for example, travel directness, which basically describes how roads are formed in a certain area. So how many one-way streets do we have? What is the security of these streets, etc., etc., etc. And this will give us some information about what is the length of a tour that we need to perform within that area. And so by using this granular input data that is aggregated on segment level, we are then able to produce high-resolution last-mile network design models and inform decisions with regards to the facility, with regards to the allocation of segments to different facilities, and with regards to the modal choice per segment. So as you can see in these pictures, these pixels that we have defined, that we have characterized in input data, are then used in a network design model to perform those different decisions. So we'll, for example, for each of those pixels, determine what would be the optimal size of type of the vehicle. And just to give you an idea, in this specific project, we have considered over 2,000 different pixels. So we do allow our model to capture highly granular input data while still making approximations that allow us to make this problem solvable. So what I've described here was a very basic network design problem, and it is the illustrations I've used is relevant to this one specific project, but is really representative of a way that we approach this for many of our projects in the realm of urban logistics. Now we can think about some potential extensions that we can make to this network design problem. And these extensions will, for example, look into a way that we can integrate some of the new trends in terms of logistics operations, business models, et cetera, into these network design models. And so before going into that part of the presentation, again, a question from our side. In your opinion, what trend is most likely to disrupt last-mile delivery operations? Here, unfortunately, I do not think there's a right answer. It's more to get a sense of what is your current understanding of this field.
Okay, and the option is our facility automation, crowdsourced deliveries, the use of drones for last mile, and also autonomous ground vehicles. So students are starting to answer. So some are saying a tie between crowdsourced deliveries and drones.
Mm-hmm.
Others are saying autonomous ground vehicles.
Yeah. I can see that it's pretty well distributed.
Correct.
Yes.
And it's varying.
Yeah.
Okay. I would say divided between the last three, and just some of them are saying that facility automation.
Yeah. So indeed, there is not a right answer. In a few following slides, I will try to illustrate how we think that some of these trends are going to impact the way that we design networks, and then also touch upon how does this impact the type of models that we are producing. So what are the implications for the models that we are developing in for network design problems? So indeed, there are a few trends that we can consider. First one, and that I have not mentioned here, is with regards to the product exchange options that e-commerce operators or parcel operators can offer to their customers. So increasingly, we see that parcel and e-commerce operators are proposing new product exchange options. So, for example, a pickup at a store, a pickup at an automatic locker, and then we also have some other delivery options that are technology-enabled, such as smart homes or deliveries towards trunks of cars. And so, if you look at this first part that looks at the product exchange options with regards to, for example, automatic lockers or pickups at stores, what this means is that we are actually required to introduce an additional layer of facilities in our network design model. So far, we had a two-tier distribution network with distribution centers and satellite facilities. Now we have to consider these additional facilities, such as lockers or stores, and to integrate them in our model. And We can also think about it in a more proactive way, and if we are looking for a model that aims in maximizing the profit, we can look at where should we place those different facilities in order to capture most of the demand and in order to increase the profit of a given company. So this is the first trend that is very relevant and that is, I would say, very much present and implemented today. A second trend that we can look at is relevant to the integration of multiple delivery services. So the model that I've described previously assumes that all of the customers are served on the, through one delivery service pipeline. So basically, we consolidate all the orders on a daily basis, and then we perform vehicle routes towards individual customers on a daily basis. However, if we think about some recent trends in e-commerce, we see the emergence of multiple delivery services with increasingly short delivery lead times. So we're moving from next day delivery to same day delivery and even towards instant on-demand deliveries performed within 1 hour or 2 hours. And also the location of the delivery can be changed and can be adapted in real time. So one of the extensions that we are actually working on right now is how do we integrate those different delivery services within one network design model. So we no longer characterize the demand for total parcel deliveries, but we have to characterize it with regards to each of those delivery services and introduce additional decisions with regards to what facility should deploy which services, for example. If we are then thinking about these highly responsive services, we also would need to accommodate some potential variability in the demand during one day. And we would also need to integrate inventory positions that are closer to the end customer. So again, in a typical network design model, we have made the assumption that all of the inventory is located in distribution centers that are located in the outskirts of the city. However, if we want to deploy highly responsive services, for example, 1 hour, 2 hour delivery, we need to move inventory positions closer to the customer. So we see companies that are deploying hyperlocal distribution centers that are typically located in the heart of urban areas, and that are served to deploy these types of services. Given that the location of the demand will vary according to the day, so typically during the day, people will order in the workplace in one area of the city. In the evening, it will be to their homes. We also need to introduce some flexibility with regards to the location of the inventory throughout the day. And one way of introducing that is to deploy mobile warehouse concept, which is basically a, if you look at the image here, it's basically a truck that can hold a certain amount of inventory and then can move throughout the day towards different parts of the city when and where it is needed. One trend that was mentioned in the question was with regards to the facility automation. So what is the link between facility automation and the network design? So facility automation basically allows us to better use space. And this in hand will allow us to deploy these hyperlocal inventories. So we can work not only in horizontal, but also in vertical, and potentially reduce the cost of these hyperlocal distribution centers that are situated in the heart of urban areas. A third trend relates to the new business models and the way that we are deploying our fleet. So again, in the model that I have described previously, we have used 3 different types of vehicles, and we have made the assumption that all of these vehicles are owned and operated by the company. In real case instances, we will most probably introduce an additional number of options. And some of them are related, for example, to the outsourcing of the deliveries. So we might introduce the possibilities that for some specific parts of the city, we want to consider the option of outsourcing it to a last mile specialist that, for example, operates cargo bikes that are particularly suited for a given area. For some areas of the city where we have a lower density of deliveries, we might want to consider collaborative operations with other operators that will allow us to increase the stop density and reduce the cost per stop. And then if you're thinking about this highly responsive delivery services, here we typically have a demand that is variable per day, and we want to deploy in real time a secondary network of vehicles that can be provided, for example, by crowdsourced carriers that we can integrate on the demand when and where this is necessary. And the final trend that we can consider is the integration of new vehicle technologies in the last mile delivery operations. So, of course, there is always a lot of buzz about the drones and how can we use the drones in urban areas. A lot of people, including our spectators here, see it as a way to tackle some of the problems of deliveries in urban areas. So in our lab, today we do not see drones as a solution that can perform sufficiently enough if considered separately. However, when we integrate this with other types of vehicles, and for example, when you think about combined truck and drone delivery systems, there we can kind of use the best of both worlds. So we have the line haul transportation that is performed by one type of vehicle that can carry sufficient capacity, and then the final deliveries to individual customers that can be performed by drones. And the last one would be, of course, autonomous ground vehicles for hyperlocal deliveries. So this, again, requires us to develop additional models for the routing approximations, for example, and for the routing. So how do we integrate a combined truck drone delivery system in a network design model that we have made? So this is it for the presentation part. I believe that we
have some questions. Thank you, Milena. It was an insightful presentation, and most of what you presented today was related to what we was covering in our course. So let me just stop sharing. Okay, excellent. So we have some questions from our students. So the first question that we have is the following. So when you were talking about the different factors or the different characteristics or the different features that you take into consideration to characterize a pixel, have you considered anything related to the factor? Any security factor, for example, that is could be included as well?
Yes. So the question of security is particularly relevant when we are thinking about emerging markets. So indeed, in some of our projects, we had to introduce additional constraints with regards to the type of vehicles that can be operated in certain areas of the city. So in some areas, for example, that have a very high risk of robbery, it is probably not a good idea to deploy a 10-pallet truck that is full of electronics. And so we would need to constrain the type of vehicle options that may be introduced and, for example, use smaller trucks. We can also limit the value of shipments that is carried by trucks. So that way we always limit the risk. And when we're looking at, for example, some options with regards to the product exchange, so I have mentioned automatic lockers. Again, probably not a good idea to deploy these in high-risk areas. So this is definitely one factor that can be integrated into network design models.
Okay, excellent. And how common do you think that this? So you mentioned that this is more common in Latin America. But if we talk in the project that the lab have conducted, do you have a sense in how many of these projects or what percentage have included these risky factors?
So definitely in emerging markets, so Latin America, India, etc. This is something that was given to us by the companies. So typically, companies, we interact with them in order to establish all of the business requirements, including this type. And it's typically while we discuss with them that some of these specific constraints come up, and then we think about ways to integrate them in our models.
Excellent, thank you, Milena. So we have another question that is more technical, and this question is was made by Answer. And it's asking about which solver do you use primarily?
So today in our lab we mostly use Python for the modeling, and then we use Gurobi for the optimization part, simply because the integration with Python is very seamless. So when we process the data, we use typically Python to clean it up, and then sometimes MySQL, etc., to make databases.
Okay, excellent. So basically, it's a combination of Python and Gurobi as a solver.
Yes.
Also, he's asking about what's the largest problem you have ever had in terms of the number of variables. Do you have a sense?
So so all of the problems that we deal with are typically quite large. And here for the project that we have made in Sao Paulo, we had 200 facility locations. We had 2,400 city segments, and then this can number of vehicle options, and this can yield several million decision variables for our problem. So if we, this is all linear integer programming. If we are moving towards some additional models that, for example, look at the way that the demand interacts with the supply. So for example, in case of product exchange options, here we end up with even more decision variables, and often end up in a nonlinear programming setting.
Okay, so we're talking about millions of variables. So Excel is not an option here for you guys. Okay, so in the course, Milena, so we use Excel, and also we have a couple of options, SAS and Ample. But I mean, for this size of this problem, I guess that Python it would be like the only option that they have. Okay, so Mohammed is asking another question. So this question is, how do you formulate the MILP when selecting a candidate location based on time and weight of the product? In the lectures and practice problem, we use distance.
So can you please, how do we formulate the MILP when?
When selecting a candidate location.
Okay, so to summarize, for each of the candidate locations, we have one decision variable that is binary, and that presents if this is a active or inactive facility. We can also allow for different size of facilities. We'll typically place several facilities with different capacities on the same location to allow for different sizes, and then the model will choose the one that is most suitable. And then in order to account for the size of the different orders, and so typically the volume of different shipments, we will introduce constraints with regards to the total flow of goods that is transitioning from within and outside a facility, and the size of the facility in terms of number of items, or in terms of capacity that it can accommodate. And we do a similar approach for the vehicle capacity. Okay,
got it. Thank you. So Agatha, she's asking another question. So let me read the question. She's saying, how can you manage costs or distances in your model if one stop meets more than one customer?
So if one stop meets more than one customer, this is something that we can capture with the drop size. So when we think about drop size, there are two ways in which we can think about it. The first one would be how many items per customer do we serve? So 1 parcel, 2 parcels. A second one would be how many items or customers per stop can we serve? And typically in our models, we integrate a fixed time per stop, which is linked to the time required to park, to operate the vehicle, and then a variable time per item. So here, especially in some highly congested urban areas, we see that drivers often prefer to park their vehicle and serve multiple customers on foot, even if that requires that they walk a certain distance, than to look for a parking spot for each individual customer. And so here again, we can use data analytics on, for example, stop duration, and link that to a number of customers and a number of items and the type of zone that we are working in, and produce basically a prediction model that gives us a estimated time per stop with regards to all of those different parameters.
Okay, excellent. Thank you. I think that clarifies everything. So the last question, Edmar, he's one of our CTAs, also from Bolivia. He's asking if a correlation in each of the pixel might not be a problem for optimization. Have you measured a correlation between pixels?
So when we discretize the area into pixels, given that the density of the demand within each pixel is sufficient, we can make those approximations for each of those pixels and then add them up. And so basically what happens is that you can end up with 3.2 routes towards one given pixel and then 4.2 towards a neighboring one.
Okay.
But then when you combine those two in an approximation, this gives you a very good approximation with regards to the total number of routes that are considered. So we discretize and we consider each one of them separately, but then when we aggregate the demand, this gives us a good information about number of vehicles. And there's a number of studies that show the validity of this type of approach. So this method was actually developed by the director of our lab, and he has compared the performance of our approximation with vehicle routing, explicit vehicle routing towards customers. And we show that above a certain demand threshold that is actually quite low, this approximation performs extremely well.
Okay, excellent. Thank you. Thank you, Milena, for being here. It was a really insightful presentation. Just a final remark, guys. So remember that we are releasing exam next Wednesday, October 31st at 1500 UTC. So the material that we'll be covering during the in the exam is going to be the first 4 weeks, so from week 1 to week 4. And you will have, the exam is going to be open for 1 week, but you have only 4 hours to complete the exam. Okay? Thanks again for joining this live event, and see you in the next one. Bye-bye.
Thank you, and good luck on your exams.